Hi everyone and welcome to this new video. In this video I want to continue my BSCP guide, so the videos that I'm doing to help you prepare for the Burst Suite Certified Practitioner certification. And in this video specifically I want to talk about HTTP Request Smuggling, which is a very interesting vulnerability. It is not a trivial vulnerability, it is one of the most complex one in the labs and in general. And so in this video, I want to introduce the idea behind HTTP request smuggling, and I want you to showcase how you can complete the first two Portswigger labs on request smuggling. The first one requires the content length transfer encoding technique. The other requires the transfer encoding content length techniques. And of course, I will discuss what they are, how they work in detail, and things of the sort. So as always, I hope the video is useful. I hope you get something out of it. If you do, please feel free to subscribe and support me. And there is also a Patreon for those of you who wish to support me also economically. It is very important for me. I thank you very much. I hope the video is useful and enjoyable and you get something out of it. So let's discuss about the idea of request smuggling, which sometimes it is the most confusing aspect of it. So request smuggling happens in systems that are complex, in systems that are made of multiple components. For example, when we typically analyze the security of a simple application, we just have the client and then we have the server and then we have the web app. So we have a simple component like where there is a single server. I mean, most of the time the web application and the web server are in a single component, so you do not differentiate the two. However, it is still important to differentiate. The web server is the component responsible for dealing with HTTP requests. The web application instead deals with other aspects like authentication, session cookies, logic business, and things of the sort. But typically, we only have a single server when you're testing locally, when you're testing a simple infrastructure. Now, when you're testing production infrastructures, when you're testing something more real that you see in the real world, this is no longer the case because you do not just have a single web server component, you actually have multiple web servers that are placed in a pipeline, in processing pipelines. For example, you might have another sort of simple layout that is still more complex than the usual, made up of two entities, of two components, a front-end component and a back-end component. So in this case, we would have the front-end component is the first one that receives the HTTP request from the client. Its job is to understand the request and then forward to an internal component, to the backend component. And then we find the backend component, which is going to be the second entity that reads the same HTTP request. This time, of course, the request is not sent from the client directly, but it is forwarded from the front-end component. And the objective of the backend is to just give it to the application so that the request can finally be processed, an answer, a response can be obtained, can be computed, and then the response can be sent back to the client. So basically that's the idea, and we can schematize, we can sort of visualize graphically as follows. A simple graph with three nodes where we have the browser, then the first web server, and then the second web server. Now, what's the idea here? What's the catch? Well, the catch is that since we have multiple web servers reading the same HTTP request, there might be differences in how this request is read by the two components. Specifically, the front end and the back end might interpret the request, the same request, in two different ways. And these differences could create inconsistencies. And inconsistency is the root behind all vulnerabilities. Is the fact that one component thinks that the request is made in a certain way, the other component thinks it's made in a different way. It's sort of you think it's the same object, right? But the way you see it is actually different. Like for example, one might see a circle, another a rectangle, but the bytes you start with are the same. This is because, of course, computer science is complex and you can assign multiple meanings to the same sequence of bytes depending on how you interpret it. And this is the root idea behind all request smuggling. It stems from the inconsistencies in how we view the bytes of the request. So This can lead to another, like, what's the end goal of an HTTP request smuggling attack? Well, the idea is to smuggle a malicious request inside another request. So basically, the idea is that we want to send two requests, but in such a way that the front end only sees one big request, while the backend sees two smaller requests. So the idea of this is that one request is not going to be seen by the front end. The smuggled request is not going to be seen by the front end, which means that if the front end implemented access control, some kind of checks, some kind of validation, some kind of firewalling rules, then when you smuggle a request, you are effectively bypassing all those checks. So that's the idea. This can lead to access to confidential resources. It can also lead to session hijacking, because by messing with this queue of messages, basically, you can desync a client and you might be able to read the response that should have been sent to a victim client. And maybe in this response, there is session information like a session cookie or things of the sort. It can also lead to cache poisoning, because once again, you are messing with the queue of requests and responses. So you might make the victim client view a different response, and in different response, there might be malicious input injected, like some kind of XSS payload, for example. So that's the idea. Like it can be dangerous. It's not easy to exploit. It's not easy to find, but it can be dangerous. There can be impact. So there are many different techniques on doing request smuggling, depending on what is the inconsistency between front-end and back-end. So today we will see two basic techniques that are called content length transfer encoding, CL.TE, and also we find the opposite, TE.CL, transfer encoding content length. Now, why are these called this way? Well, basically it's because in content length transfer encoding, for example, the front end will actually read only the content length header to determine the size of the request, while the backend will only read the transfer encoding header to determine the size of the request. Since they use different headers, we can trick the front end into thinking that we have one huge request and the backend into seeing two different requests. So that's the idea, basically. Now, of course, it's important to realize, however, that these are just two main techniques. There are a lot of different techniques, so there are potentially many different ways to smuggle a request. The objective, once again, is to smuggle the request to make sure that the request is only seen by the backend and not the front end. And this sometimes happens with this kind of complex systems. So let's get started with the first technique, which is called content length transfer encoding. And for doing this, we will showcase the first Pursuit lab on the HTTP request smuggling labs. So we open the lab and we just start it. So we wait for it to start. So the lab is started and I've copied it into the Pursuit browser so that we can analyze with the proxy. So let's open the proxy now and let's see how to do this attack. So here I'm gonna clean the history that I had because I don't need it anymore. I'm gonna refresh it once again and I'm gonna get this into repeater. So I have this request. Here it works perfect. Now, before showcasing with burp, actually, let me walk through the creation of the payload. So in this kind of attack, CL.TE, we assume the following configuration. The front-end server supports HTTP 1.1 and uses the content length header to determine the size of the request. The backend instead supports the transfer encoding header to determine the size of the request and also supports the HTTP 1.1. So the payload is constructed as follows. We start from a basic post request using the HTTP 1.1 protocol, so the 1.1 version, because with HTTP 2 things are more complex. So we start with a basic post request. Why do we need post? Because in post we can always put the body. Sometimes we can also do that with gets. These are called fat gets. However, this is not always available. So while with a post it is always available. So that's the idea. Then we add our content length header. So we add the content length header to this first request. Now, the value of this header is a critical thing and we must be really careful on how we compute it. In this case, it's actually easy to compute because in this attack, the content length header has to specify all the bytes, including the bytes of the second request. So we must see it as a single block. This means that to compute this value, we can actually let the burp suite compute it on its own with the automatic computation that we will see in a bit. So we don't really need to worry about this content length specific value. Then we add a transfer encoding header with the value chunked. Then we add a first chunk of size 0 to the body, so that there's only a chunk of size 0, so like this. And finally, we put the smuggled request after new lines, after 2 new lines, actually after 1 new line. And notice that this inside request is the smuggled request, so this is another request. So, and finally, we can resolve the value of this content length, which in this case is gonna be 35. Why is it 35? Because it's gonna pretty much be all these bytes. And here, this caret m is just for the carriage return. So carriage return a new line, basically, just to visualize the carriage return. So basically this content length is going to be 35 and we can actually let burp suite compute it on its own. So this is our final payload. Now let's take a while to understand it because it's really important to understand why it works. So what's the objective? The objective is to smuggle the second request, right? So let's see this request from the point of view of the first web server, the front-end component. So the front-end component processes the content length header, and this content length says 35 bytes. So the front-end component is like, okay, these are the headers, this is the start of the body, and this is the end of the body, I have 35 bytes, okay. So the front-end component sees this as a single whole message. So that's the front end, and it sends these bytes to the backend component. Now the backend component starts reading the request, but the backend component ignores the content length and only processes the transfer encoding, remember. So the backend is like, okay, here I have a transfer encoding chunked, and it's gonna look for chunks, and then it's gonna see a chunk of 0. Now a chunk of 0 is used to and a chunked message. So the backend component is going to be like, okay, this is a whole message. At this point, I'm good with this message. And then it sees the other request, this other get request. And then it's like, okay, then I have this get request, and which means that the backend component sees 2 different requests. So that's the idea. So how can we exploit this in burp? Well, we open burp here. Remember, I have this get. So I'm gonna remove all the useless headers. I'm gonna send it again to make sure it works. I have to downgrade the protocol. So actually, let me just full screen burp so that you can see better. I'm gonna downgrade the protocol into HTTP 1. Then I have to make it into a post. Then I have to put transfer encoding chunked. Perfect. Here I'm gonna showcase the 0. Then I'm gonna have a 0 value here, and then I'm gonna have a like a get 404 HTTP 1.1 x ignore x. And so this is the message itself, and I can let burp update the content length here automatically. I send this, you're gonna say 35. Look, here it says 200 okay. How do I know if I've actually smuggled something? Well, let's make another request. Let's make a different request in here, right? So let's make a different request and let's send this request. Notice that here I got 404 not found. Now, why do I get this response? Well, I get this response because once this request is sent to the backend was still processing this smuggled request. So this request is going to essentially end, like these bytes are going to end this smuggled request, and so what it sees actually is the get/404, which means that the response I'm getting here is not due to this request, it is due to the request that was smuggled by the attacker. And here we can already see some kind of dangerous effects of smuggling a request. An attacker here can put whatever he wants, a malicious request, and this malicious request is sent to the next victim, the next person who just loads the website. So this is also why this can be used to poison the cache, because maybe internal cache components can say, okay, here I have this response, but this response does not really match this thing, it matches another request, it matches the /404 request. So that's the idea basically. So if I send it again, of course, I'm gonna be done. The queue is not gonna be broken anymore, and I have the normal response. But here I can put anything basically, and this is gonna work. Of course, if I put more stuff here, I believe it's not gonna work anymore. And why it's not gonna work anymore? Because at this point, the second request is fully resolved by the backend. And so the backend, like the request itself is just discarded. I really want to be careful that I do not terminate the second request. The second request has to be on a sort of like holding state in the backend, so that when the next client is going to give some more bytes to the backend is going to reply with the sort of like finishing touches for this request. So that's the idea for the first lab, and look at this, we have solved it. That's good. Now we can move on to the second lab, which is the TE.CL. So we can once again start the lab. Here so this is gonna be the content length transfer encoding. Content length transfer encoding, and then we're gonna do the opposite. So here, let me clear the history. Perfect. And before doing that, however, a quick mention to the sponsor of today, which is Infomaniac. So Infomaniac is supporting my project throughout this year. So they offer me a VPS and the Git server that I offer through Patreon subscription, which you can find at git.exam.sh. So this Git server is hosted on an Infomaniac VPS. So they are really helping me out, and I appreciate that. And I'm using their service, and so far I'm finding that it's useful. It's useful. The cost is right with respect to what they offer. So what do they offer? They are a cloud provider. They have different cloud services, and for example, they offer this low cost VPS that start from €270 per month. So they can be very useful if you want to start hosting your own services. In general, I suggest you to check out the Infomaniac services, especially if you live in Europe or areas around Europe. They are a Switzerland company. And yeah, that's pretty much it. I just want to mention them and thank them for supporting the project throughout the year. So thank you very much, Infomaniac. And that's it. We can continue with the video itself. So we saw the first lab, CL.TE. Let's see the second lab, TE.CL, transfer encoding content length. Now, in the second lab, we have the opposite situation. So the front-end server actually uses the transfer encoding header, while the backend server uses the content length header. Once again, we're talking about HTTP 1.1. Why do we need this? Because in the HTTP 2 protocol, the length of a message is not determined by these fields, but it's determined in a different way, and it sort of like removes most of the smuggling vulnerabilities. At most, there are ways in which the front end supports HTTP 2, but the backend supports HTTP 1, and so you can still smuggle a request because the backend is vulnerable. But in general, if you upgrade to HTTP 2.0, I don't think you can smuggle requests, or if you can, it's gonna be much harder. So that's a good fix, that's a good remediation, let's say. So in this configuration, we have transfer encoding for the front end, content length for the backend. So how do we construct the payload? Once again, we start with a basic post request. Why do we need post? Because posts have bodies. Sometimes also gets have bodies, but not all the time. In this case, we can just start with a post. Then we add the content length header. Now remember that previously the content length header was computed automatically by birth suite. We can compute it automatically by birth suite, and it was just the amount of bytes in the body itself, which was 35 in our case. Now this time the content length must not be computed automatically by birth suite, therefore we have to disable such automatic computation, and I will show how to do it later on in the video. So for now we'll just put a placeholder value of X. Then we add the header transfer encoding chunked with the transfer encoding with the value chunked. Then we add a first chunk. So before we just added a chunk of 0 with nothing, and now we add a chunk of a certain amount of bytes. So this certain amount of bytes, once again, is still to be resolved later on. So for now, we'll just put Y, and then later on we will actually compute it. And then here we put the smuggled request. So post, and then with the content type, content length. So notice that also the content length has to be resolved. And then, so this is the smuggled request. And finally, we add a second chunk of 0 to terminate the request. And so we are done with the request itself. Now, at this point, we are almost done. We do have the structure of the payload. However, we need to resolve three values, which is the length of the smuggled request, the length of the first chunk, and the length of the outside request. And remember, this time, the front end only sees the transfer encoding chunk. The backend will see instead only the content length. So the first thing is that we need to resolve this the size of the internal smuggled request. So how do we do that? Well, the idea is that we're gonna see the size so far that we have in the body of the bytes here, in the body of the smuggled request. This is gonna be 10 bytes, all the things that I've selected, so 10 bytes here. So this is 10 bytes. And in the content length, we need to put something greater than 10. Why do we need to put something greater than 10? Because the idea is that we don't want to fully resolve the second request. We want to make sure that the backend waits for more bytes, at least one more byte coming from the client. In this way, the victim client will receive the response to the second request. And so, at this point, we have resolved the content of the smuggled request. So now we have to resolve y and x. So at this point, we need to resolve a y. Now, y is the size of the first chunk. Now, the first chunk is pretty much the smuggled request itself. So it is all the content that is before the 0, the last chunk. So this is gonna be 94 bytes. It is the region that I selected in the editor, as you can see here. It is right after the size of the chunk and before the last carriage return. So this means that in hexadecimal we have a size of 5e, which means that here on the y we write 5e because this is the size of the chunk. And last thing, we need to put the content length of the external request. Now, what's going to be this content length? Remember that the backend is the one who reads the content length. So that we want to break this single request into two requests for the backend. This means that in this content length, we cannot put the entire body, because if we put the entire body, the backend will not split it properly. We just need to put enough bytes here to signal this line. So this is 4 bytes. So it means that here we're gonna put pretty much 4. And so this is the final request that we will send. So basically, this is the final request that we have. Once again, let's review together why it works, why it allows us to smuggle the second request. So the front-end server will read this and will use the transfer encoding to determine the length. And it's gonna notice, look, we have one chunk of 94 bytes here, and we have a chunk of 0 bytes. So we end with the chunks. So the front end is gonna see this entire thing and it's gonna forward it to the backend component. The backend component is gonna read the same thing, however, it's gonna interpret it differently because it's gonna use the content length as a means to break up the request. And it's gonna say, look, I have a post request of content length 4, which means that this post ends here. And then I have a different post of content length 11, which means that actually, even after it has read all these bytes, the backend will still wait for more bytes to come. At this point, the victim client comes in and sends more bytes. It ends this request, and so the backend responds to the victim client with the smuggle response, pretty much. So that's the idea. Now, let's see. So let's see. Okay, this one I have to access it again because I had to do something else, and so the lab expired. So let's wait a little bit for this second lab, which is the TE.CL. So let's copy it into the burp browser so that we can play around with burp suite. So let's do it in here, I suppose. Let's do it in here. Is it 0H2? 0H2, perfect. So we put in repeater. So how do we exploit this? Well, first of all, we remove the useless headers. We downgrade to HTTP1. We transform this into a post. Then we write transfer encoding chunked. At this point, so we were saying, what do we have here? We have to write the size of the transfer encoding, 5e. So it's 5e. Then we write post 404 HTTP 1.1. We put content type and content length again in the chunked here. So here pretty much we have to copy this and we have to put it here basically. Then here we put a space x equal 1 space 0 and then the 2 like this basically. So the last thing we need to do is we need to disable the automatic computation of the content length. So we want to not update it automatically. Here we write 4 because it just has to consider these 2 bytes. And here we write 11, which is greater than 10. At this point we send it, it's gonna say 200 OK. But if we send this request again, notice that it says not found. It says not found because we have smuggled the request. Therefore, now we are seeing the response to the smuggled request, not to the original request. So basically, we're seeing the response to this internal post request. So that's the idea. I send it again. Notice, once again, I get the 404 not found. So that's the basic idea of HTTP request smuggling. The idea is to smuggle a request so that the backend sees 2 different requests, while the frontend only sees one big request. And this can allow for a variety of attack. So the Portswigger Labs, they offer different scenarios in which you can practice this. These are just the first 2, and then there are many others, basically. So there are like a lot of different labs. But the idea is what I described. It's just that the way it's done can be very different, can be more complex. But the basic idea is the same. I hope this video was useful. I hope you got something out of it. If you do, subscribe to the channel, share this video and this channel with like-minded people. Thank you very much and to the next video.